All right, can you guys hear me? All right, yeah, my name is Michael Erb, and I also did some research on drought. So my talk is about constraints on US drought dynamics from the Last Millennium Reanalysis. I did this work with Julien Milget at USC and others at University of Washington, Oregon State, and elsewhere. So just to start, I'm sure you guys have seen this figure before. It's from the most recent IPCC report. It's just mean temperature variations over the past 2 millennia. And I just want to show this to make 2 points. One, there is a lot of interesting climate variability during this time period. And two, there's a fair amount of disagreement between these different reconstruction methodologies. And they're not all reconstructing exactly the same thing. Some are just land, some are land plus ocean, but there's still considerable variability. I also wanted to say, this just shows temperature. But we're not just interested in temperature. We're also interested in things like precipitation and drought and all sorts of things. And that's something the Last Millennium Reanalysis can help us get at. So this morning, Greg went over this figure. I won't spend long on it. Just to say that, yeah, for the LMR, we have 2 sources of information. One is our climate model prior. We also have information from a lot of different proxy records. And basically, all of the temporal information is coming from these proxy records, whereas the model prior helps us fill things in spatially and also helps us translate from whatever variable the proxy is recording into our entire climate state for things like 500 millibar heights and drought and all sorts of things. So this morning, we also talked about these Breton-Moser trees, whether to use them or not. And Greg hasn't been using them. I have been using them for this experiment here. So you can see this is the, these are all the proxies that I've been using for this research. This is what Julien was talking about. There are 3 sources of information. One is the Pages 2K version 2. We also have several thousand Breton-Moser tree ring width and some additional records from NCDC. And there are some criteria for which ones I use. They need to have at least annual resolution. They need to be at least 40 years in length and have overlap with the instrumental record, since that's how we're doing the calibration. And for the proxy system model, I'm using linear regression against the instrumental record. For most types of proxies, I'm using linear with temperature. For the tree ring width, I'm using bilinear with both temperature and moisture. And so you can see that it's, quite a nice assortment, especially over North American land areas. And so here's our verification against temperature. This black line is the LMR temperature, whereas the colored lines are various modern reanalyses or instrumental data sets. You can see we have correlation values of about 0.9, CE values, that's that coefficient of efficiency that Greg mentioned. Those are about maybe 0.5 or 0.6. And you can see it's doing fairly well. There are a couple little biases. The slant on this line is a little bit too high in the LMR. This is still a little bit work in progress. I'm going to rerun this experiment. And I'm confident that I can have a better verification score there. But it shouldn't change any of the results that I'm talking about in this talk. So, like Sloan, I want to talk about drought. Drought affects things like agriculture, fire hazards, sustainability, and much else. And primarily, I want to look at how was the US drought influenced by large-scale climate patterns. And before we get to that, you guys probably don't need to be convinced, but let's talk about the consequences of drought. So this is some data from NOAA NCEI, formerly NCDC. These are billion-dollar climate events over the past 38 years. You can see there are things like drought, flooding, freezes, tropical cyclones, all sorts of things. And of these billion-dollar events, there's been 24 drought events. They've cost the US almost $250 billion in damages. And if you combine it with deaths from heat waves, there's been almost 3,000 deaths. In both those categories, it's second only to tropical cyclones in the scale of the disaster. So I don't think I need to convince anybody, but yes, droughts and heat waves are a considerable important event in the US. And if we look farther back in time, droughts have had effects on people over the past millennia or two. So these have been mentioned before. These are the so-called medieval megadroughts, which proxy records indicate that there are these long-lasting periods of drought from the 10th to maybe the 13th centuries. And these droughts, together with some internal conflicts, are suggested to lead to the mass migration of the Anasazi people out of the American Southwest. So these people, for instance, they had the Mesa Verde community, as well as a variety of others across the Southwest. So this was probably just one factor in why they left, but it was probably an important factor. So Sloan introduced the North American Drought Atlas. That's Ed Cook's database. It uses several thousand tree ring records and a statistical method to calculate PDSI, the Palmer Drought Severity Index, over North America over the past millennia or two. And so in reconstructing drought with the LMR, the first thing I wanted to do was compare how the LMR does against the North American Drought Atlas over this 1,000-year period. And I've calculated two things here. On the left is the correlation between these two data sets, and on the right is the coefficient of efficiency. I've also overlaid, these are all the proxy records in this area that are being used in the LMR. There are also proxy records being used elsewhere, but probably these local records are contributing the most impact on drought in this region. And you can see that for correlation, over the US, the correlation between these two data sets is quite high. And coefficient efficiency looks pretty good as well. Now, once you get into Canada and parts of Mexico, the agreement isn't as good, but the North American Drought Atlas has trouble in those regions too, so I wouldn't worry about it too much right now. And besides, we'll be focusing on the US. And there is quite a lot of overlap between the data sets used in the North American Drought Atlas and this work, but they've been detrended in different ways, and these are very different statistical techniques. So if we look at this a different way, here's a time series averaged over the US region with the North American Drought Atlas in black and the LMR drought in blue. And the error bars come from the LMR as well. And you can see that both in the timing and magnitude of drought events, these two data sets are very similar. If we focus in on a specific region, the Southwest, again, you can see these events in magnitude and timing are very similar between these two events. And this is pretty remarkable, I'd say. So what is drought connected with? This is a strength of the LMR method, is that we're not just reconstructing temperature or just reconstructing drought. We can reconstruct really anything that's in the model prior with various amounts of uncertainty attached to it. So I want to look at how drought in the US is connected with larger scale climate patterns and later on external forcing as well. So drought has been hypothesized to vary with ENSO, the Atlantic multi-decadal oscillation, and internal atmospheric variability, as well as some other things. So I computed a maximum covariance analysis. This is a bit like an EOF, except instead of just looking at one field, you're comparing two fields. And you're asking the algorithm to say, what patterns explain the maximum amount of covariance between these two fields? And the two fields are what you see. It's drought over the US region, and then SSTs over a wider region. And what's important to point out here is I'm not asking it to say what explains the most drought in the Southwest. And I'm not asking it to say what's related to ENSO. These are just the patterns that it picks out as explaining the maximum amount of covariance between these two fields, which is drought in the Southwest is related to a La Nina pattern in the equatorial Pacific, as well as kind of a cold PDO pattern in the North Pacific. And so that goes along with traditional thinking, that La Ninas encourage drought in the Southwest. Another way we can look at this is if we take now we're looking at precipitation. if we take the 15% of the driest years and the 15% of the wettest years in the southwest US, what are the other climate fields during those years? You can see that again, when we have dry conditions in the southwest US, we have cold eastern equatorial Pacific, La Nina conditions, as well as these anomalies in 500 millibar height. We have a high pressure there, a blocking high. And the opposite conditions, when you have wet in the southwest US, you pretty much have the opposite in SSTs and heights. You have more of a El Nino conditions, as well as lower 500 millibar heights. So this is in keeping with traditional thinking about drought and ENSO. Here during El Nino, we have a more zonal jet stream across the Pacific Basin, which brings those storm tracks across to the west coast, gives us some rain. Whereas the La Nina, we have this blocking high pressure system develop associated with the La Nina, which diverts those storm tracks more northward. So we end up with a little bit more rainfall more toward the north, and in Southern California and the southwest US, we're left with drier conditions. So it's good to see that the LMR, over the past millennia, it supports this conventional thinking about La Nina. And I showed those results. That was from the entire millennial period. But if I broke it down century by century and did the analysis for just a 100-year period, for every century, you see essentially the same result, that La Ninas are associated with drought in the southwest. If we look at individual years, though, here's individual years. We have Nino 3.4 on the x-axis, precipitation in the southwest US on the y-axis. You can see that correlation. You can see the La Nina conditions and drought, or reduced precipitation down here, going to El Nino and increased precipitation up here, and with an R-squared of about 0.2. So you can see there clearly is a correlation there, but there's also lots of scatter. So there's lots of variability that's not explained by this relationship. And so what does explain that remaining variability? So Sloan gave you a little bit of spoilers for this part, but I looked at precipitation versus external forcings, these three. CO2, we have volcanic aerosol optical depth, and we have solar forcing. And here's what these forcings look like over the past 1,000 years. And what I did, a pretty simple approach to see whether there's a direct relationship between these forcings and precipitation in the southwest US. And so what I did was I calculated a multiple linear regression between precipitation and these three forcings. Then I computed, based on that regression, computed the portion of the precipitation time series that's linear related to these forcings. So we have two forcings now. We have two time series now. We have the original LMR precipitation time series, and we have the component of it that varies linearly with these three forcings. And those two time series, I computed R-squared between them to see what amount of precipitation these three forcings explained, and I computed R-squared at every grid point in the LMR. So an R-squared of 1 would mean that the forcings explain everything, whereas an R-squared of 0 mean they explain nothing. And again, I'm talking about a direct response. So like if a volcanic eruption happens in 1 year, is the precipitation affected in that year? I'm not talking about the effect that solar forcing or volcanic forcing might have on the eventual dynamics of the climate system like Sloan was talking about. But you can see here, these R-squared values are really fairly low. For global mean, they're 0.04. For the southwest US, they're 0.03. So that's barely anything. So the question, does precipitation in the southwest US seem to be a direct response to external forcings, is largely no. It's not. And so what's left? Remaining variability might be a nonlinear response to these forcings, or more likely a lot of it is the result of internal atmospheric variability, which isn't the most satisfying response, because we'd like to have a larger degree of predictability on these drought responses. And internal atmospheric variability is harder to predict on large timescales. But yeah, that definitely seems to be the answer. So before I wrap up, I want to talk about a slightly different topic as well related to drought, because the LMR does provide us with a nice several thousand year time series of droughts. I wanted to use it as a test for climate models, particularly in the length of dry spells. So how do droughts in models compare with the LMR? So I'm looking at dry periods. And here, again, I've done what Sloan did a couple years ago in one of his papers. I've defined a dry period as a period where we have 2 consecutive years of below normal precipitation, and it ends when you have 2 consecutive years of above normal precipitation. And so I'm going to compare this, the lengths of these dry spells, against output from multiple GCMs, Last Millennium simulations. We have CSM, TSM4, a variety of others. And this is what it looks like. So what I've done is I've counted the number within this 850-year period of, we have 5 to 9 year dry spells, the number of those, the number of 10 to 19-year dry spells, and the number of dry spells that are greater than 20 years. And I've also done, in addition to the Southwest US, I've included a couple other regions that are typically examined in drought contexts, the Northwest, the Central US, and the Southeast. So the box and whiskers plot that's black, that's for the LMR. That's the range of numbers of these sorts of dry spells you get over a variety of iterations of the LMR. That's another way we sample uncertainty in the LMR, is you can run a variety of iterations that use a different subset of proxies and also different years to the prior. So it gives us a range of our uncertainty here. The blue box and whiskers is the CESM. Since there's a variety of last millennium simulations from that, we can have a range of uncertainty there. All the colored dots are the other models. And you can see approximately the range you get from those. And really, when looking at this, it kind of depends if you're a glass half full person or a glass half empty person. So in general, the models do agree pretty well with the LMR. I should specify as well that the LMR isn't relying on model physics to determine the length of these dry spells. The LMR is getting the length of these dry spells explicitly from proxy records. So it's a nice test in that we're using a completely different source of information. And in one sense, they agree very well. The LMR and the models, in general, they're pretty similar. Especially these middle length ones are very similar. Even once you get to long ones, they're not too much different. However, if you're a glass half empty person, you might say, okay, the LMR is showing more long dry periods. There aren't really all that many of these long dry periods in the GCM results. So it depends a little bit how much you trust the LMR as well, but this could suggest that the models aren't capturing these long dry periods quite as well as they should. So conclusions. The LMR agrees well with instrumental temperature records and the North American Drought Atlas. On average, drought in the Southwest US is associated with La Nina conditions. However, this relationship only explains part of the variability. If you remember, that scatter plot showed quite a lot of scatter. Much past precipitation variability does not vary linearly with external forcings. Some of that remaining variability might be nonlinear, or it's the result of internal atmospheric variability. Dry period length and GCMs generally agree well with the LMR, but they show fewer long, which I mean 20-year plus periods of reduced precipitation. All right, thanks. Any questions?